Hello, Sioux High Earth Science students. This is Mr. McLeod again. Welcome to the finish of Part 2 and the final Part 3 of our Introduction to Astronomy. In this screencast, we will continue our discussion of some astronomy basics, things you will need to know in order for us to get a deeper understanding of our place in our universe and in the cosmos as well. So get your notebooks out and let's do this thing. We will finish the last section of Part 2 by trying to get an idea of just how large our own universe is. Once again, we'll use the light year as our unit of measurement. So click on this video link and answer the questions I provided you in Moodle. Remember, you can pause it at any time or even go back if you missed the information to answer the questions. Okay, so open the study guide in Moodle and let's answer these important questions. If you have questions while you're watching, raise your hand or write them down and we'll answer them for you. So start the video now. Okay, now that we know how really big our universe is, let's explore the idea of how old it is. We're going to use a time measuring device you are familiar with, namely a calendar. Remember now, our universe was formed about 13.7 billion years ago. So if we use that as our starting point and apply it to our 12-month calendar, how many years would each month represent? So get your calculator out and see if you can figure that out. If you used your calculator, you got that each month represents 1.14 billion years. If you ballparked it, you probably said that each month represents about 1 billion years. Both are correct. But let's use 1 billion for each month. It's a nice round number. So if we divide this number correctly, we see that each day on the calendar represents about 30 million years. So write that down in your notes. Each day represents 30 million years. If we divide this number further, we see that each hour in the day represents roughly 1 million years. 30 million divided by 30 gives you 1 million years. And that works out to each second representing 20,000 years. So get these measurements down in your notes so we can answer some important questions. Now, if you look at this diagram above, you can see some significant events and when they occurred. According to our calendar, the Big Bang occurred on January 1st. Based on the fact that our galaxy was formed in February, estimate how long it took for our galaxy to form. So think about that, and then we'll talk about it. If you estimated it took about 1 billion years for our galaxy to form, you're correct. It took 1 month. 1 month in our calendar is equal to about 1 billion years. Now, question number 2. How long was it before our Earth formed? Take a look at this calendar and estimate how long it was before the Earth formed, and we'll talk about it. If you said it took about 9 billion years for the Earth to form, again, you would be correct. According to our calendar, it took 9 months for the Earth to form. Because each month is worth 1 billion years, that would be 9 billion years to form. Now, question number 3. Take a look at the calendar and see if you can tell how long before life on Earth formed. Take a look at that and we'll get back to you. This one may have been a little tougher. Remember, modern humans have only been around on our planet for roughly 200,000 years. So now that you have that number, try again. If you said about 10 seconds, you'd be right. That's 200,000 years divided by 20,000 years for each second would equal 10 seconds. So, let's see here. Compared to the age of our universe, 13.7 billion years, or in calendar 12 months, we modern humans have only been on Earth for 10 seconds? Man, does that ever make me feel younger. Woohoo! Okay, that finishes part 2 of our intro. Let's move on to part 3. Hopefully, everyone has some frame of reference for the motion concepts we are going to introduce here. Most people know that things are moving in the sky, but they really don't understand what they are seeing, and more importantly, why they are seeing it. For example, you could prove to most people that the sun moves in our sky every day just by observing it. It rises in the east, moves all day until it sets in the west, day after day after day, without fail. Our days get progressively lighter from dawn until around noon, and darker from noon until dusk, day after day after day. Even though we really don't actually feel the earth moving, it most definitely is. We are not sitting still, as the slide above mentions. Let's outline some basic motions and try and quantify them. In other words, give them a speed if we can. First, the idea of rotating. Just like a merry-go-round, the Earth rotates around its imaginary axis, meaning aligned from the middle of the North Pole to the middle of the South Pole, once every 24 hours. You can see the imaginary axes right here on this diagram. So one axis would be right here, right through the middle of the North Pole. You see the person standing there. And then there'd be another axis right here through the South Pole. So again, it takes the Earth 24 hours to rotate once around its axis. Now, what about how fast it rotates? Well, take a look at the planet, the globe, in this diagram, and see that it depends on where you are on the planet. If you're standing on the North or South Pole, it wouldn't feel like you were rotating at all. However, the closer you get to the equator, the faster you would be rotating. Now, answer this question. About how fast are we rotating where we live? Take a look at that globe and see if you can answer it. If you looked at the globe, you would see that we are rotating at about 1,275 kilometers per second. Now, since there are approximately 1.6 kilometers in a mile, that's roughly about 1,000 miles an hour. Now, you've got to be thinking, if we're moving that fast, wouldn't we feel it? If the Earth's rotating at 1,000 miles an hour, wouldn't we feel it? That's a great question. Now, the reason we don't feel it is because everything on the Earth is moving at the same rate. Therefore, we really don't notice it. Like our example we've given in class of two cars side by side on the highway going 55 miles per hour. To the passengers, they would look like they aren't moving at all, and it would feel like they aren't moving at all. It's the same concept here. Okay, now motion number 2, the idea of revolving. Now we know the Earth rotates around its imaginary internal axis, and this causes day and night. We just talked about that. It takes 24 hours. However, Remember that the Earth also revolves around the sun, meaning that the entire planet makes a single revolution around the sun approximately every 365 days. We call that time period a year. Write this in your notes if you need to. You can see the path the Earth takes around the sun in the diagram above on the right. Question for you. Take a look at this orbit path in that diagram and see if you can explain what makes the shape of that path wrong. Go ahead, think about it. If you said that the shape is incorrect, you'd be right. The orbit paths of the planets, including our Earth, are not perfect circles, they are ellipses, oblong shaped like the shape of an egg. Okay, 2 new terms to write in your notes and understand. First, perihelion. Write that term in your notes. You can see the spelling above. Then describe it as the nearest point to the sun the Earth is in its orbit path. So take a second and write that down now. Now write the term aphelion. Again, you can see its spelling above. Then write that it's the furthest point from the sun the Earth is in its orbit path. So take a second and write that. Now I would challenge you that most people believe the seasons are caused by the difference in distance of the sun from the Earth. They would believe that summer occurs at its perihelion, where it's nearest to the sun, and that winter occurs at the aphelion, or the furthest point from the sun. What's interesting is that it's the exact opposite. Write this down. When the sun is at its perihelion, it's winter. And when it's at its aphelion, it's summer. Just the opposite of what people think. So get that in your notes. Well then, what does cause the seasons then? Take a look at the diagram on the bottom left. Write this in your notes. The Earth's axis is tilted 23.5 degrees to the orbit path it takes around the sun. Again, the Earth's axis is tilted 23.5 degrees to the orbit path it takes around the sun. Write that in your notes. Also in your notes, write that the Earth's axis points toward Polaris. The Earth's axis points toward Polaris, so write that in your notes. Also write that Polaris is called the North Star. So write that in your notes as well. Polaris is called the North Star, and we'll talk a lot more about that later in this class. Lastly, and this is important, write that it's the tilt of the Earth that causes the seasons, not how close or far away it is from the sun. Write that it's the tilt of the Earth that causes the seasons, not how close or far away it is from the sun. Now motion number 3. Let's take a look at the diagram above on the left. Remember that most stars are located in groups or clusters. Write in your notes that we call these clusters of stars a local solar neighborhood. Remember, solar just refers to star. So get that in your notes. Now that's a good way to describe it. A neighborhood is a cluster of houses all on the same block. Motion number 3 is that our sun moves relative to the other stars in the local solar neighborhood. So write that in your notes, that our sun moves relative to the other stars in the local neighborhood. Take a look at the box in the diagram above. We're talking top left. It represents all the stars in our sun's neighborhood and their motions. Just like in your neighborhood, your neighbors move relative to your house all the time, and you move relative to theirs. This is how stars act in their local neighborhood too. So if you need to write that explanation in your notes, do it now. Okay, motion number 4. We're now looking at the bottom left of this slide, or bottom right of this slide, sorry. This motion is not like your neighborhood, so the comparison stops here. Our sun and all the stars in this local solar neighborhood all orbit or revolve around the center of the Milky Way galaxy. Make sure you write that in your notes. Also write that orbit takes an astounding 230 million years. So it takes 230 million years for our neighborhood group of stars to orbit the center of the galaxy. Wow, imagine if that were the time period for our year. Man, would I be younger then. Not even close to a year old. Woohoo! Okay, sometimes I know I act like I'm not even a year old, but that's different. Okay, so let's move on. Okay, last motion to understand. This motion has to do with the idea that our universe is expanding. Our galaxy, the Milky Way, moves with the expansion of the universe. Write that down in your notes right now, that our galaxy moves with the expansion of the universe. How do we know this? Through the development of technology, we can actually chart the movement of galaxies from day to day, month to month, and year to year. What we have found is that most galaxies appear to be moving away from us. We call this movement red shift. Write that in your notes right now. That red shift is galaxies appearing to move away from us. Now we'll explain that in more detail later in this class. But for now, write this down as the explanation for red shift. In fact, we can make this conclusion from scientific observation. The further away a galaxy is, the faster it's moving. Write that in your notes now as well. We can use a familiar example to explain this motion. Take a look at the diagram in the picture above. If we think of putting raisins inside a raisin cake dough and then putting it in the oven, just like is pictured above. As the cake bakes and rises, the raisins all move apart from each other as the dough expands, just like in this picture. The raisins in this cake have all moved from 1 centimeter apart to 3 centimeters apart because of this expansion. Make sure you write this down in your notes. You'll need this example in the future. Okay, now let's review what we've learned in this introductory series of podcasts. Now I'm going to read this information, but you need to write it in your notes in case you missed something. So let's take a look at what we've learned in capsule. Remember, you can stop this and write if you don't have something in your notes. or you can pause it. So please feel free to do that. All right, we started out asking the question, what is our physical place in the universe? And in that vein, we learned that Earth is a planet in a solar system, which is one of some 100 billion star systems in the Milky Way galaxy. So if you don't have that number, put that number in your notes. There are 100 billion star systems in the galaxy. Now this galaxy is one of about 40 galaxies in what we call the local group. So in our local group is about 40 galaxies. Now that local group is a part of something called a local supercluster. So make sure you have that in your notes, local supercluster, and then those superclusters make up the universe. So make sure you have all that information in your note. Then we wanted to describe our cosmic origins and why we say that we are star stuff. And in that vein, we said that the universe began in the Big Bang, and that produced only two chemical elements, hydrogen and helium. And that the rest of the elements have been produced by stars, which is why we are all star stuff. So make sure you have that in your notes as well. Then we look at the idea of why looking into space means looking back in time. We said that light takes time to travel through space, and we talked about a light year. Thus, when we look further away, we see light that has taken a longer time to reach us. So the further away an object is, the longer its light takes to reach our eyes. Therefore, the older it is. Then we looked at what our solar system looks like when viewed to scale. We used a 1 to 10 billion scale. And with that scale, the sun was about the size of a grapefruit. Now that meant that the Earth was the size of a ballpoint, or we said the head of a pin, and Jupiter the size of a marble on this scale, and that the distance between planets are huge compared to their sizes. And we talked about how far each planet was from each other in terms of meters or yards. So make sure and check that you have that in your notes. Then we looked at how far away the stars are. And we used that same 1 to 10 billion scale, in that the nearest stars to the sun would be thousands of kilometers away, like Alpha Centauri, and the rest of the Milky Way must be viewed on a different scale. It would take thousands of years to count them all. Then we talked about human time scales and how they compare to the age of the universe. And we used a cosmic calendar, just like a regular calendar, 12 months. And on a cosmic calendar that compresses the history of the universe into 1 year, human civilization is just a few seconds old. I believe we used the word 10, or the number 10 seconds. So make sure that's in your notes. Then we describe some basic motions of our spaceship Earth. We talked about that the Earth rotates on its imaginary axis, the one that goes from north to south pole, once each day or 24-hour period. And that it takes the Earth 365 days to revolve or orbit around the sun. We call that measurement a year. We said that it took our own solar system 230 million years to orbit the center of our Milky Way galaxy. We also referred to galaxies in a local group that move relative to one another, or neighborhoods, while all other galaxies are moving away from us with the expansion of the universe. So check and make sure that's in your notes as well. And then we talked about how we knew the universe was expanding. We said we observed nearly all other galaxies to be moving away from us, with more distant ones moving faster. Okay, so that ends our introduction to astronomy in this class. We laid out some basic concepts that we're going to be referring back to when we start talking about more in-depth motions, more in-depth objects, more in-depth ideas of what we see in the sky. So thanks for listening. We'll talk to you soon. This is Mr. McLeod signing out.